Okay, we're going to work at three different special right triangle examples. One of them is a 60, 30, 90 degree right triangle, and this one is a 45, 45, and this one has a 90-degree angle, but we don't know what these angles are, and we don't care because we're going to use Pythagorean theorem to figure that out. On this one right here, the 60, 30, 90, we're asked to find both variables, m and n, and we're given the longer side. How do we know? Because the 60 degree, opposite the 60 degrees is the longer side, and the shorter side is n. Immediately we know the relationship between the shorter side and the longer side, this is being the shorter side, is that the longer side is √3 times the shorter side. So n equals √3 times the shorter side. √3 times n equals 2 √3. And that we know from our ratio, which is 2, 1, √3. And again, I'll say it again, is that we're looking for n. We do know one thing. We know that the longer side is 2 √3 and that √3 times n is equal to this. This is a true statement, and we work with that. Now we're going to solve for n. We have to divide by √3 on both sides. And then we get n equals to 2. Simple as that. And the key to this was being able to set this up properly, and the key to knowing how to set these equations up is understanding the ratio. And then just putting it in algebraic form. So, and once we know n, we know m because the hypotenuse is twice the shorter side. So m equals 4. And that's our answer for this special right triangle, 30, 60, 90 degrees. Over here to the 45, 45, 90, we've got two variables we're looking for, x and y. And we do know that the hypotenuse is x and that √6 is one of the sides. Then we know that y is equal to √6. That's because of the ratio, which in this case is 1, 1, √2. So we know that whatever this side is, the other one is equal to that. Now we know that x is going to be equal to √2 times √6. Why? Because we know the shorter side is √6, and that because of our ratio, that whatever this is, the hypotenuse is √2 times that. So I'm going to do this down here. X equals literally √2 times √6. That's it. And now you have to know a little bit about radicals. You have to remind yourself, how does that work? You could do this two different ways. You could break this into √2 √3, and because radical 6 equals √2 √3. We have a double, we get 2 √3 as our answer. For those of you who don't remember that way, the other way you can do this is by going or. You can get √12, which is equal to √4 √3, and that's equal to 2 √3. At this point right here, √2 √6 is equal to √12. So it just depends on how you have learned to do radicals, how you've learned to solve them and simplify them. But either way will work. Either way, as you can see, you get 2 √3. There it is. And now, last but not least, this triangle doesn't tell us what the angles are here. We just know there's a 90-degree angle. And so we use Pythagorean theorem, and c squared in this case is x squared. So c squared equals a squared plus b squared, with c being the hypotenuse. So we really have x squared equals 5 squared plus 12 squared. And it really doesn't matter which one you label a or b, because in the end we're going to get the same thing. We're going to put these together. X squared equals 25 plus 144. And this x squared is going to equal 25, and 144 is equal to 169. And we take the square root of both sides. X is equal to 13. And that's your answer for that one. So this is a great example of special right triangles, and also right triangle which uses the Pythagorean theorem to solve for it. 30, 60, 90, 45, 45, 90, and a 90-degree triangle with unknown angles here, all solvable with either the formulas, ratio formulas, or Pythagorean theorem. Incidentally, an interesting note is, if you didn't want to use these ratios, you could still solve these two triangles with the Pythagorean theorem. You don't have to actually use these ratios. They're meant to make things simpler. But you could actually solve these just by using c squared equals a squared plus b squared. Of course, though, you would only be able to do that if you were given two of the sides, and in this case you aren't. But after, for instance, you found one of them, like for instance you have y, root 6 and root 6, you could have used Pythagorean theorem by going c squared, in this case x squared, equals, and let's look at that, x squared equals root 6 squared plus root 6 squared. That's one way you could do it, a squared plus b squared. And then here you go, you get x squared equal to 6 plus 6, x squared equals 12, and you take the square root of both sides, and you get x equal to root 12, which is equal to root 4 root 3, which is equal to 2 root 3. So, as you can see, these are meant to be shortcuts and are useful in a lot of ways. You're not always given two sides, so you have to figure it out. Maybe get one extra side, then you have your two sides. You're bound or you're willing, you can go ahead and try the Pythagorean theorem also as a check to see if their answers are right. And that gets overlooked. A lot of times students go ahead and they solve these and they're always not quite sure whether they got it right on a multiple choice or whatever kind of test. But if they would just use the Pythagorean theorem with two of the sides, then they would feel more at ease in knowing that they got the right answer. And if they got the wrong answer, they'd do it again. All right, good luck with those.